2. Okay, let's go. So limits and discontinuities. Okay, so in calculus, when you are doing the chapter on limits, which is typically the first chapter, you're going to run into these discontinuities. And I know that, I have done some videos, okay, and if you're, going through my site, you'll find them. But here I wanted to expand a little bit and include limits and also talk about some particular discontinuities which can happen at some x is equal to, for instance, a. Okay, so first, before we dive into discontinuities, so here is the table that I kind of utilize with regards to, so the left-hand side is basically, a limit as x is approaching a of some function f at x exists, okay, if the three conditions hold. So the left-hand limit exists, the right-hand limit exists, and they're equal to each other, okay? So the left-hand limit is equal to the right-hand limit, okay? So that's what we would have right there. And if these three conditions hold, then we know that a limit at a exists. Now, on the opposite side, on the right-hand side, we see the continuous kind of properties that we need to hold. So first, okay, we need to have our function be defined at x is equal to a. We need to have our limit, okay, so basically the left-hand side has to hold true. And then finally, the limit has to be equal to what the function is at that point a. So those conditions have to hold. And basically, if you're looking at these conditions, if something is discontinuous at a, one of these falls apart. So doesn't matter, okay? So one of these, I guess 6 falls apart. So if you don't have a left-hand limit, then clearly you won't have a limit at all, right? So it can't be continuous. So that means it's going to be discontinuous, and so on. So you can glance at these. I don't on the left and then on the right, and if one of them falls apart, you're finished. It's basically discontinuous. That's what it means. Now, a very nice way of thinking about kind of intuitively, especially when you're just starting, you pretty much do everything, in 2 space. So you don't have variables that are more than that. You just have your x, your y. Okay, so if you're independent and dependent variables. And then, if you're drawing out your function, so the way that you can think about that is, if you can draw the function, so if you can trace the function along with never basically leaving, okay, if you're drawing it with a pencil, and, you never leave, okay, the pencil unattached. You don't have to actually lift your pencil somewhere else, right? So, we can draw a nice continuous function. Of course, there's a little bit more because we don't want to, run into some other issues. But as soon as you have to leave, so like if I go on and I have to now lift my pencil, okay, it doesn't matter what it is, maybe because it's not defined here, so I would have to lift my pencil, and then maybe, I would continue on here, and I would go in this way. As soon as you lift that pencil off, you're creating some kind of a discontinuity at that point. And that's how you can think about, and oftentimes teachers will talk about this. I think I remember one of my teachers actually mentioning this. Okay, so it's the whole kind of test. Can you trace out the function without never having to leave your pencil? So lift your pencil. If you have to lift your pencil off, you're going to be creating some discontinuity. All right, so that's kind of the introduction. Now, jumping into the types of discontinuities. And so here, we have a discontinuity at x is equal to a. And there are 3 particular ones that you're going to run into. I hope that you're going to run into, and your teachers will explain this to you in some way. Or you're learning that through this particular video. So here, you either have a jump discontinuity, you can have an infinite discontinuity, or you can have a possible removable discontinuity. So let's talk about these a little bit. So here they are visually. So for instance, a jump discontinuity means that you do have your actual kind of limits existing, right? So your left-hand limit exists, your right-hand limit exists. Now, your overall limit, so if you're looking at these three, okay, so these particular three graphs, okay, you'll notice that, okay, well, the left-hand limit here exists, right? The right-hand limit will exist. The overall limit at that A will actually not exist. And notice that we do have a jump. So as you go from, the left or from the right, you'll jump. You either will jump up, or if you're going from the right down, you're going to be jumping, okay, downwards. So you have a jump discontinuity at that point A, right? We would have to lift our pencil in order to draw or trace this thing out. Now, it's actually defined everywhere, but there is a jump that happens. And there's all kinds of different jumps, so they don't have to be just flat lines. You can see here, I can carry myself along in here, I can trace back, and notice that, it looks like, I actually do have a left-hand limit here. But, as soon as I go, okay, and I try to touch this, basically this will jump all the way over here. And from here, if I continued, it would jump down, and then I would have to continue on in this direction. So the limit for this one does not exist. The limit for this one does not exist. So that would be enough to tell us that the function is discontinuous at A. And now the type of discontinuity is a jump discontinuity, because as we're going along, we're basically jumping to one point or sometimes another, and then continuing on our way. So that would have been another example of a discontinuity. The third example here, this is actually kind of neat, because as you're going along in this direction, your left-hand limit exists, right? And if you would have been coming down, the right-hand limit actually also exists, and they are equal to each other, right? So they're basically coming into the same point. So the limit exists, right? So that's one thing, so that's great. So the limit as x is approaching A of our function actually exists. We know what it is. Great. Now, the function also exists, okay, at A. So if I go back in here, it is defined at A for this. However, what does not hold is that these two, so our limit, okay, and our function at A are not equal to each other. So that's where it breaks apart. So we have a discontinuity. And also we have a jump discontinuity, because as you're carrying yourself along either in this direction, you're going to have to jump in order to put that and place that point there. So you're basically jumping down, and then you're going to be jumping back up, okay, in order. So you're going to be jumping here, okay, and then you're going to be jumping back up if you wanted to continue in this direction, or vice versa. You're going to jump down and then jump back up. So those are jump discontinuities. And in all of these cases, the function was actually defined at that A, but we still had a discontinuity. And an infinite discontinuity, so here's a couple of examples, so this one and this one, for instance. So what happens here? In infinite discontinuities, what you will find, okay, so here, for instance, we have our A, I guess it would have been at 0, so, you can kind of trace this back and up, so it looks like, this is blowing up on the infinite side here, and then it's, this is going to be going up and blowing up in this direction. So notice, if we try to find the limit as x is approaching A from the left-hand side, so we would be going in this direction, that limit actually does not exist, right? So that limit does not exist. It would have been tending towards negative infinity. And so that's what happens. If either you're left or possibly you're right, or both, like we have in this case, so actually both of them, as we're approaching it from the right, this blows up and it would actually go into positive infinity, right? So if either left limit or the right limit or both of the limits blow up on us, so they go off into infinity, okay, then we have an infinite discontinuity. Notice the function is not defined right, it is actually not defined here because we have an asymptote, okay, that we're going to be approaching and we actually never get there. So that would have been an infinite discontinuity. There's an infinite jump here, right? So in the previous case, we were actually jumping to some point or some line, but in here, we do not jump anywhere. We just go off and we just keep carrying on infinitely, right? If we were coming from the left or coming from the right, we would just blow up upwards. On the right-hand side, so this one is pretty neat because as we're going on the left-hand side, okay, again, so this is my A. So in this case, if we're going in this direction, we do see that a left-hand limit exists. And then it looks like we have a jump discontinuity right here. So it jumps over to whatever value that might be. So I guess, we could read that off. I didn't specify it there. So we have a jump discontinuity as we're going along. However, we also have an infinite discontinuity if we're coming along from the right-hand side. Because on the right-hand side, as you go on, it looks like this function just blows up on us again. So the right-hand limit does not exist, and it blows up to infinity. The left-hand limit exists, and then we have some kind of a jump. But this function is defined at A, but it has a discontinuity. So it has a discontinuity, right? So within here, so we have that jump, so either going in this direction, but, okay, as you can see, so along here, there's no jump at all because it would be infinite, because as it goes up and blows up. So we have two. There's a there's a jump discontinuity, and then there's an infinite discontinuity as well. And then this, removable is next. It's the last one. This one's a little tricky, especially when you actually have to solve for it. So I'm showing you these visually so that you can see. Ultimately, we will be talking about some limits in just a moment. So a removable discontinuity occurs when we have a situation like this. So this is very similar. So as you can see here, this was this case right here, right? Where both the left-hand and right-hand limit exists. Okay, so here we can actually say, so the left-hand limit, so in this is what it would be. So this is my A. So the left-hand limit exists. The same thing is true. So X, okay, at A, okay, so notice the right-hand limit exists as well, because if we're going along in this direction or we're going along in this direction, they both do exist. And the overall limit also exists, right? Because these two are equal to each other. So that means we have a limit here. So our limit exists. However, we have removed, so hence removable. So it's not defined at A. So F at A does not exist. And therefore, it's discontinuous. It's discontinuous at that point. And it's called removable because when the function is not defined at that point, but the limit exists at that point, then we say that that is a removable discontinuity. We see the same thing here. So notice from the left-hand side, we're carrying on. From the right-hand side, we're carrying on. So we have a removable discontinuity at A right there. We removed it. It's, function is not defined there, but the limit exists there. And then here, so if I would call this B, we also have an infinite discontinuity at that point. So for this function, there's two discontinuities that we can see here. So I hope that this gives you a visual sense of understanding what these mean. Now, I have several examples here for you, so I want to be able to walk us through these examples and see, do these limits exist, do they not? And then, what kind of discontinuity do we have here? So here's my first one. So I prepared several examples for you so that you can see, and you might, run into this. So if I run into this, Okay. Now notice what I can do is, so this limit, I can use limit properties. If you didn't watch that video, I'll put up a link up above there. So it was a pretty lengthy video on understanding how to show the limit and limit properties. So within here, I know that I'm going to run into trouble, right? But I could, so technically, so I can say, you know, this is limit. Okay, I'm going to bring that 3 out. This is going to be of x. Okay, so I'm using the limit properties within here. So that's what I'm going to have there. And then this would have been the limit of x plus the limit of 1. And what I would find out, so, you know, this right here, this is just -1. -1 squared is 1, so I would get 3 on top. And then in the denominator, unfortunately, so, you know, here I would get -1 plus 1, and I would get 0. So we get undefined. And if you recall, okay, if this happens, then the limit does not exist. If the limit does not exist, that means that this function is discontinuous. Right? So it's definitely discontinuous. Now, what kind of discontinuity does it have? Now, you can do it by graphing or by sketching. So if you still remember how to sketch. Now, I can see that this particular function, if I sketched it out, right? So if I put this out, this x plus 1, so at -1, this would actually have an asymptote, okay? Okay, something like this. So I know I'm going to be running into some kind of trouble within here. Now, let's pop this up into decimals. Okay, so I can certainly sketch it out, right, around that area, and I can sketch the entire thing, okay, to be able to see what happens. But I want to pop up decimals just so that you can also see it, you know, visually in a very nice way. And this is going to be, you know, an infinite discontinuity that we're going to be running into. All right, so let me pop this up. Okay, so this is a function. Let's call this function 1. X is equal to, so this is 3x squared all over x plus 1. And so now let's do this, and you can see here, it shouldn't really surprise you, okay, within here. That's what we would have. So we do indeed have an infinite discontinuity, and we can tell that, right, whenever you apply your limit properties and you run into an undefined result. So a number divided by 0. Okay, so this is an infinite discontinuity. If you had to, you know, map it out with respect to, you know, something if a teacher has asked you. So here is another example. So this is example number 2. So this looks like it's a piecewise, some kind of a function. So let me copy this, bring this down. So here it is. And we're trying to take the limit, okay, of this function as x is approaching 1. Now, you know, do we run into a problem here? So, well, so first of all, so I mean, for x is less than 1, so this looks like it's some kind of a parabola. So again, you know, we can sketch. I mean, I can certainly sketch this one out. This is just a quadratic. So notice it has just a translation in here. You know, so an original parabola. So this is for x is less than 1. So this gets shifted. This is 1. And then it gets brought down to -1 over here. So basically, it's going to look something like this. Okay, and it blows up over there. Okay, so this goes off. So that's because it's a parabola. Okay, so that's what would happen there. And then this right here, so this is for x greater or equal to 1. So it's equal to 2. So let's say this is 1, this is 2. So basically, you know, now this is just a constant. So this is going to look like this. So within here, you know, limit as x is approaching to 1. Well, from the left-hand side, so notice if we wanted to take the limit as x is approaching from the left-hand side, then this would have been just taking, so x minus 1 squared minus 1. You know, I could certainly take that result and then see what that leads to. So if I would do this, okay, so I would have substituted. So in terms of that, so the limit of x is just equal, so at 1, so this would have been 1. So 1 minus the 1 squared minus 1, this is 0. So it's actually -1, which is no surprise as we're going in here. But the right hand, okay, because it's a constant, so from the right hand side, the limit is actually equal to 2. So the limits are not equivalent, so this limit does not exist, right? So left hand side and right hand side limits are not equal, and the function would be discontinuous. And it looks like it's a jump discontinuity. So this would have been a jump discontinuity for this one. And, again, we can certainly graph this as well, although I already did it as a plot. You can put it up in decimals if you like for yourself. Okay, so here's another one. So this one right here. So I'm going to copy this down. And then let's take a look at this one. So let's find the limit as x is approaching to -1. So what do we run into? So I'm going to use the limit properties here. So if I do that, this is going to be a little annoying because I'm going to get limit of x squared, minus the limit of x minus, the limit of 2 all over. So we would have, limit again, x squared plus limit of 2x, and then plus limit of 1. So what we're going to run into here, so I'm going to just kind of fast forward in here to try to find these. So we simply just get 0 over 0. Again, we could, simply just plug this in here, but I just wanted to show it to you. So, through the utilization of the properties. And now what we said is when you run into this problem, when you have 0 over 0, which is indeterminate, you actually cannot conclude if the limit exists or not. This does not mean that the limit does not exist. It just means that you can't determine it. So indeterminate, so it means you can't determine it from the method that we just used. Okay, now actually, so within here, so what I'm going to do now next, I'm going to try to massage this and see what happens. I do notice that I have a quadratic on top and quadratic at the bottom. So let me factor that out. So this goes back to your quadratics, and if you remember how to factor them. So you have x, I guess this is going to be minus 2 and x plus 1. I think that's what that would be. And then here, this is going to be x plus 1 and x plus 1. So that's x plus 1 squared, right? So that's just factoring out the quadratics. So if you've forgotten about quadratics, and how to factor these, maybe I'll put up a link up above there. Typically, it's kind of grade 9, grade 10 results, but it is useful here. Now, if I look at this, now notice, I want the limit as x is approaching to -1. When we say x is approaching -1, it never actually is -1, right? If that's the case, look what happens. This x plus 1 and x plus 1 can actually cancel within here. So that's something that can happen. And once I see that, so now I have x minus 2, and then I have an x plus 1 at the bottom. And now if I try to take the limit as x is approaching to -1 within this case, right? So I basically cancel those off. Now what I'll have is if I take the limit and I start applying the property, so I'll get limit of x minus limit of 2 all over, okay, limit of x plus limit of 1. So this is going to be pretty neat because now what's going to happen is this -1, right? So we have -1 minus the 2, and then here this is -1 plus the 1, so that's going to be 0. So we're going to get -3 over 0, and that is right here undefined. Now, what happens when it's undefined? Well, when it's undefined, we know that the limit cannot exist. So if we, originally what we did, we started here, and the limit was indeterminate. But now as we factored it out, okay, we basically found that this is undefined. And now let's plot it. So what that would mean, if it's undefined, that means there's some kind of an asymptote, okay, that is happening in here. So let's try to do that. Put it up in decimals. F, call this the second function. Okay, x is equal to, and we have, I'll put it all in brackets, x squared minus x minus 2 all over x squared plus 2x plus 1. And there you have it. So we do run into a problem, and we do indeed have, okay, so here, an infinite, once again, infinite discontinuity. So it just starts to blow up on us. Now, this may not always be the case. If you're using this trick where you factor things out, it may happen that, for instance, because of the cancellation that you did, so this cancellation, the limit for this might exist. Now, for us, it didn't. We got undefined. But it can happen that that limit actually exists. And then what you would have is, you would have a removable discontinuity for that. Okay, so you can try to pay attention. And I think that the next example actually shows something like that. So let me go in here. So here's the last example that I have for you, which is this one. Now this one is super weird because it has radicals. So let me copy this. Now, if I take the limit, this is approaching 0.5, so I can already see I'm going to run into a problem because 0.5 minus 0.5 is 0, right, at the denominator. So I'm going to run into a problem there as I take the limit. Now, in the numerator, so what I have is, this is going to be 2. Well, 2 times 0.5, so that's 1. So that's 1 minus 1. So again, I'm going to run into the problem of having indeterminate. So I don't know if this limit exists or not. So I have to do a little bit more. Now, in the previous case, I had a quadratic, so I could factor things out, and that was great. But what happens when you have something like this and you can't factor it out? So here's what I recommend that you do. So this is kind of a trick, and if nobody ever shows you, you would run into a problem because you wouldn't know if the limit exists or not for this case. So the trick is, the one that I like to use is, okay, so I notice, this is, negative. I have the radical over here, which I don't really want. So what I like to do is I like to multiply and basically create a difference of squares to get rid of that radical, right? So I would get 2x plus 1. And again, so this comes from the fact that, x squared minus y squared, for those who remember, okay, this is what the difference of squares is. It's x, right, minus y multiplied by x plus y, or, x plus y times x minus y. That is the difference of squares. So I hope that you do remember that from your earlier years in math. And I will do that. So if I do this, now I have to do it to both numerator and denominator because I can't change the overall result. So doing this is going to give me, so this is going to be, I guess, 2x, because it's this right here, right, minus, this is going to be 1. Okay, so that's what I will have on top. And then in the denominator, I have 2, and then this is x minus 0.5. I don't know, let's see if this works. So times, now I have this mess here. So that's what I have there. Let's see, let me bring this 2 inside. Okay, perfect. So if I bring that inside, I'm going to get 2x minus 1 all over 2x minus 1 right? And then I have this mess here. So that cancels all together. And now I have 1 all over just this, 2x plus 1. And so let's see if that will help me as I'm approaching 0.5. Yeah, it does help me. So within here, now the limit, so the limit of the top is equal to 1. That's just a constant. And then the limit of this, okay, is basically, you know, the square root of 2 times the limit of just x. So that's 0.5 times 2. So that's 1. And the square root of 1 is 1. So this is 1 plus 1, which is 2. So the limit is actually a half. So that's neat. So this means that this must be a removable discontinuity. So we have removed the discontinuity within here. So that's really neat. So if the limit exists, okay, so here's the, you know, for removable discontinuity, the limit has to exist. And it does in here. But if you would, so if you take the original and you substitute for the limit, you get an indeterminate result. So if you get an indeterminate result and then you massage the function such that you find that the limit exists, then that's a removable discontinuity. Now let's plot this so that we can see, you know, how does this look like. I want to be able to see. So let's say it's called this function 3 equals, so square root of 2x minus 1. Let's put all of this in bracket. Divided by 2x minus 0.5. All right, let's see what this looks like. Probably some mess. Now we're approaching, yeah, we're approaching 0.5. So notice, like you can't even see it on decimals, right? But here, as we approach 0.5, yep, there we go. Look at this. So the function is undefined there, which makes sense. That means we have a removable discontinuity, but the limit exists. And it's a half. And indeed, it is a half, right? We're approaching a half from both the right and the left. So I would encourage you to try it. So those are some examples. I hope that by watching this video, you know, you have an idea of kind of the removable discontinuity, the infinite discontinuity, and then a jump discontinuity. You know, you can try those out and then you can walk yourself through these, plot them out in decimals, but also try the limit properties to see what happens. All right, thanks for watching. We'll see you in a future video. Bye, everybody.